Okay, we are talking about torque here. This first example of the Achilles tendon illustrates the simple definition of torque, which is that, well, I wouldn't say this is the definition of torque. This is the definition of the magnitude of torque, which equals RF sine of phi, where phi is the angle between the radius and F, and the radius R is the connection between the attachment of the force and the axis point. So it's going to be that ankle joint there. So we're going to connect this arm here, and that is R, where R equals 3.6 times 10 to the negative second meters. And phi is this angle between the two. So then, in order to determine the torque, magnitude, and direction of the force about the ankle joint, we would say that torque equals, well, RF sine of phi. We have R, we have F. R equals 3.6 times 10 to the negative second meters. What is phi? Well, because this is a right triangle here, and we have, let's call it theta, we want to find phi, then phi equals 90 minus theta, right over here. The phi equals 90 degrees minus 55 degrees, which equals 35 degrees. So the magnitude of the torque is just 3.6 times 10 to the negative second meter times 790 newtons times sine of 35 degrees. If you calculate that out, that equals 16.3 newtons newtons times meters. But now the question also asks, what is the direction? I think of the direction of the torque. I think probably the best thing to do here is to just say the magnitude is that and the direction is clockwise. Because this torque tends to pull around clockwise. You could also say the torque is equal to negative 16.3 newtons per meter, because negative is in the clockwise direction, but either way would work. Okay, so in this example, we have a person standing on the diving board. Now, you won't get diagrams like this in the problem, say, on a test or on the homework. So you'll be able to, you need to know how this diagram is constructed. So you have the force of the weight, I'll call that Fg. You have the fulcrum pushing this way, and you have the force of the bolt pushing down here. Let's go ahead and redraw it on another sheet of paper so we can kind of start fresh. There's the diving board. You have the force of the fulcrum. You have the force of gravity, and you have the force of the bolt. You also have some distances here, but let's think about this now. The force of the gravity equals 530 newtons. The length of the diving board is 390 meters, and the length from the bolt to the fulcrum is 1.40 meters. Okay, so probably, well, maybe, okay, let's think it's at equilibrium. So at the conditions set forth by being at equilibrium are that the sum of the forces are equal to 0. That's stuff we've covered previously. And we also know the sum of the torques is equal to 0. Well, let's work with the torques first, because we can't do anything with the forces yet. We have two things that are unknown and one thing that is known. So, well, I'll show you that. The sum of the forces equals negative FB, because it's downward, plus the force of the fulcrum minus the force of gravity equals 0. The problem is we know this, we don't know that, and we don't know that. That's two unknowns. We can't solve that equation. We can't do anything with it. But we can work with the torque. That is equal to the torque of the bolt, the torque of the fulcrum, and the torque caused by the gravity of the person. Now, I left spaces here because we don't know if these are positive or minus or negative yet. We haven't yet chosen our axis. But I'm going to expand this, go ahead and expand it, as RB, FB, sine of phi b. I'll explain what all this stuff means in a second. RF, FF, sine theta f, and RG, FG, sine theta g. Again, no positives or negatives yet because we haven't determined which way we're going to consider the rotation. So, this is at equilibrium. So since it's not moving, we can choose the axis to be any point on this diving board that we want it to be. We can choose it here, we can choose it here, we can choose it here. You're probably going to get the inclination from the start that it's either going to be line up with one of these forces. Now the question is, which way do we go? If we were to say, choose this as the axis, let's choose the axis being where the person's standing, then that R is going to be 0, and this term's going to go away, and then we're left with two unknowns here, the force of the bolt and the force of the friction. That does no good for us. We need to use our axis to eliminate one of these unknowns. So I'm going to choose the axis right here. I could have chosen the axis right here. That would work too. Just for some reason, I chose it here at the fulcrum. So what that means is that we can now go in and decide if all this stuff is positive or negative. So that means the force of the gravity is going to induce a clockwise twist to the diving board about that axis. So that is going to be negative. The force of the bolt is going to be counterclockwise, so that will be positive. The force of the fulcrum, I'm just going to put a positive in there. It's not going to matter. You'll see in a second. It doesn't really have a direction because it can't cause a torque. And it can't cause a torque because RF equals 0. The distance between the force and the axis is 0 because the force is applied right at the axis. So that term is 0. The distance between FB and the axis is 1.40 meters, and the distance between the weight of the person and the axis is going to be 3.90 meters minus 1.40 meters, or RG is just equal to 2.50 meters. Okay? So let's rewrite this. RB, FB, sine phi b, plus 0, which is RF, times FF sine phi f, minus RG, FG sine phi g. Okay? As we said, this term's going to go away because it's equal to 0. What are these angles? Well, you know, they're all directed downward because the board is horizontal. So those are 90-degree angles. So phi b equals phi g equals 90 degrees, and sine of 90 degrees equals 1. So the sum of the torques is equal to RB FB times 1 plus 0 minus RG, FG times 1, and all of that equals 0, remember, because we're at equilibrium. Well, remember, we know what this force is, we know what the radii are, and we're solving for the force on the bolt. So I'm going to add this term to each side. RB, FB equals RG, FG, and the force of the bolt is equal to RG over RB times FG, which is just equal to RG, 2.50 meters, over RB, which is 1.40 meters, times FG, which is 530 newtons. And our answer is 946. Well, now we found one of the unknowns. So now we can solve the second part of the problem, which is finding what the force of the fulcrum is. We can do it several different ways. I can move the axis, and then either whatever axis I choose, as long as it's one of these 3 points, I'm going to have just one unknown. So I can solve it that way, do the torques again, or I can do the much simpler thing, which is look at the sum of the forces, which is actually the sum of the forces in the y direction. So I have a negative FB because it's pointing downward. I have a positive F of the fulcrum, and I have a negative FG, the weight of the person. We know what FB is because we just solved that. So let's solve for the fulcrum, which we don't know currently. So that's just going to be FB plus FG. Well, FB we solved for at 946 newtons, and we're going to add to that 530 newtons. So FF is just F for the fulcrum. It's equal to 1480 newtons. So a key thing to note here is that you'll notice that each of these are positive, but the forces are working in a different direction. Well, that's because we're only working with magnitudes. And we're only working with magnitudes. What I mean is that I'm inserting negatives to show where the direction is. So the sum of the forces in the y direction, really you're adding all the forces, but then when you calculate it out, this is going to be a negative. But I'm just talking about the magnitudes, and I'm inserting a negative in front of the magnitude to show, because I know it's working downward. So that's why my answer is going to be positive. But I know that is just the magnitude. The direction is going to be, well, positive for the fulcrum, but negative for the force on the bolt. Okay, let's look at the bodybuilder example. The guy's holding a dumbbell straight out. The weight of his arm is 31 newtons, and it's got a center of gravity right here in the middle at this location, 0.280 meters from the shoulder joint. The deltoid muscle here can supply some force, and it's operating at an angle phi of 13 degrees, and it's attached to the arm at 0.150 meters from the shoulder joint. So the question asks, what is the weight of the heaviest dumbbell she can hold? So we need to find the weight of this dumbbell, corresponding to that maximum force by the deltoid muscle. Well, there are two ways you can think about this problem. you can think about it as, well, this muscle is a force that has two components. One component is like this and must cancel out the force on the shoulder in the horizontal. And the other component is like this, and that's applying some torque around the shoulder joint. But another way to look at it is just ignore this force because it's in the horizontal, and just look at the torques, knowing that this torque is going to be equal to the force times the distance from the axis times the cosine of phi, the angle the force makes with the lever arm. So since I introduced torque that way, that's the way we will do it. Let's start by starting from scratch, drawing our diagram. We have, I'm going to call this, use my own notation, Fm, force of the muscle. And there's Fs, force of the shoulder. Fg, the weight of the arm. And Fd, the weight of the dumbbell. Okay, we could add all these forces up, but we don't know what the force of the shoulder is, and we don't know what the force of the dumbbell is, so we've got two unknowns. If we were to do the sum of the forces, we would have two unknowns. But we know it is at equilibrium, so the sum of the forces must equal 0. We know that, and we also know the sum of the torques must equal 0 because it's at equilibrium. So working with equilibrium, we can say that is, we now have 4 forces. I'm going to put this equation down here because I think I'm going to run out of room. Okay, I'm moving the question aside, but you've got the PowerPoint slides, I'm sure, so you can refer back to the question on there. The sum of the torques is equal to the torque from the shoulder, the torque from the muscle, the torque from the gravitational force of the arm, and the torque from the dumbbell. And that can be expanded as the radius of the shoulder, the force of the shoulder times sine of phi the shoulder, the radius of the muscle, the force of the muscle times sine of phi for the muscle, the radius of the weight of the arm, the force from the weight of the arm times sine of phi from the arm, g for gravity, and the radius of the dumbbell, the force of the dumbbell, and sine of phi of the dumbbell. Again, I haven't put signs in there yet because we haven't chosen a pivot point, an axis. Well, 4 locations come to mind. I don't know what this is, and I don't know what that is. So if I choose the axis here, I'm going to be left with 2 unknowns there. The same thing if I choose the axis here. If I choose the axis to be right here, well, that's going to eliminate this unknown, but this is the unknown we're looking for. If I put the axis here, that eliminates this unknown from the shoulder, but who cares? The question's not asking for it. Okay, so the axis point is right here, which means this is going to be counterclockwise and therefore positive. This is going to try to endorse a clockwise motion, so that's going to be negative. The dumbbell is going to do the same thing, so that is negative. And the force of the shoulder, well, there's not going to be a torque, so I'll just put a plus in there for now. So this RS is going to equal 0 because it's right at the axis point. So this whole term equals 0. And I can carry down the signs here. Negative. Okay, well, phi m equals 13 degrees. That's given to us in the problem. Phi G, however, is going to be the same as Phi D. They're both going to be right angles. And sine of 90 degrees equals 1. So these sine functions cancel out. So I can say the sum of the torques equals 0 plus Rm Fm, sine of phi m minus Rg Fg minus Rd Fd, and all of that sums to 0. Well, we're given from the problem that this distance right here, Rm, this is just given to us in the problem, is 0.150 meters. The distance to the center of gravity of the arm, 0.280 meters. And the distance to the dumbbell, Rd, is 0.620 meters. So we have all these radii. We have the force, the weight of the arm. I should write that down. .0 newtons. We also have the maximum force of the muscle, which is 1840 newtons. These are all the things we know. So we need to solve this for the dumbbell. So I'll just add this term to each side. So I can say Rd Fd equals Rm Fm sine of phi m minus Rg Fg. And now we're just at the point of plugging in number. Well, no, excuse me, we need to divide by Rd. So Fd of the dumbbell is equal to Rm Fm sine phi m minus Rg Fg over Rd. Or the force of the dumbbell is equal to 0.150 meters times 1840 newtons sine of 13 degrees minus 0.280 meters times the gravity, 31.0 newtons, all over the radius, which is the distance to the dumbbell, of 0.620 meters. When you multiply that out, you get 86.1 newtons. Again, we're talking magnitude, so we know this force works downward, but we're just worried about the magnitude. Okay, children on the seesaw. You have child 1 with that mass, child 2 with this mass, so you would have Fg1 and Fg2, but you would also have the force upward from the fulcrum. And this is a distance of R1 and R2. We'll write down the things we know. M1 equals 26.0 kilograms. X1 equals 1.60 meters. M2 equals 32.0 kilograms. X2 equals, we don't know that. Actually, I'm sorry, I should have used R. And the force of the fulcrum, we also don't know what that is, but we're looking for that. That the distance of the second child first. So the sum of the torques, let's choose an axis point. I'm going to choose right here. That seems like the most logical, but it's also, because we don't know what the force from the fulcrum is, it eliminates that unknown. So the sum of the torques is equal to the torques 1 plus torque fulcrum plus torque 2. And all that equals 0 because they are at equilibrium. So torque 1 is R1 FG1 sine of phi1 plus 0 because RF is 0. And minus, and that's minus because this tends to induce a clockwise rotation from this force here. So let's say minus R2 FG2 sine of phi2. Well, we know these are, so this goes to 1 and this goes to 1 as well. And we all know that that all sums to 0. So R1 FG1 equals R2 FG2, and R2 then is equal to R1 times FG1 over FG2 equals 1.60 meters times FG, well, excuse me, let me back up here just a second before I plug in numbers. We don't have the weights, we have the masses. So that's R1 times M1G over M2G. G's cancel. So it's R1 M1 over M2. Or R2 just equals 1.60 meters times 26.0 kilograms over 32.0 kilograms, which then equals 1.30 meters. Now the next question asks, was the force exerted by the pivot? Well, we can just sum up the forces and say negative Fg1 plus the force of the fulcrum minus Fg2 equals 0. The force of the fulcrum then is equal to Fg1 plus Fg2, which equals M1G plus M2G, or G times M1 plus M2. And, whoops. The force of the fulcrum then equals 9.8 meters per second squared times 26.0 kilograms plus 32.0 kilograms. And that all equals 568 newtons. Okay, let's talk about this one for a second. This one we didn't work in class, and you know what? I'm not going to bother working through it here. The solution is on my wall. This just gets to some nasty geometry, but the reason I think it's a useful and kind of clever little problem is that it makes you really think hard about your choice of the axis. So when you work out the problem, well, let me describe the problem. You've got the ladder laying against the wall. This is frictionless on the wall, and this has friction on the ground. a person stands in the center of that, so he's got some gravity working downward. Now, we must choose our pivot point. We don't want to choose the center because we know what that guy's weight is. We have two unknowns, which is the force. Well, actually, we have three unknowns here. We have the friction, the force of the normal force from the ground, and the normal force from the wall. And I believe the problem asks for both of those forces. So it seems reasonable that you would eliminate one force and then try to find the other force like we have been doing. In this case, if you choose this as the pivot point right here, both of these two torques equal 0. So yeah, I suppose you could solve that for the normal force on the wall, but the problem is then when you go back and then try to move the axis over here or something, and then work with this, well, you've got two things that are are perpendicular, and the normal force of the ground, or the friction, is dependent upon the normal force of the ground. So you couldn't do that either because you'd be left with two unknowns again. However, if you choose the pivot point right here, which is just somewhere in the sky, this torque cancels out from the normal force because that is along the radius, along the straight line to the axis. This also cancels out. So you're just left with the torque from gravity and the torque from friction. Then you can work with that. Once you find friction, then it's easy to calculate the normal force on the ground because the friction is just equal to mu times the normal force. Once you find both of these forces, then you're just left with this one unknown, and you can solve that a number of different ways. But the point of this problem is just to note that the axis point is not even on the body that we say is rotating, because think about tying a stick to a string and whirling it around you. There's a torque being applied to that stick, but the axis is not on the stick. I don't know if that made much sense, but the fact of the matter is you can choose your equilibrium point anywhere you want to because the thing is at equilibrium, it's not moving. And then the problem is fairly straightforward. There is just, I have to admit, a bunch of geometry and stuff that takes a while to work through. But you might want to try working through it. It is, as you see, a 2-page solution. Oops. Okay, center of gravity. Well, if you want to treat some rigid body like a point mass, you have to start talking about its center of gravity. Where can you balance out all the torques? If you put an axis right in the middle of this arm, where would all the torques balance so that the arm balances? Okay, the equation for that, you may remember, is equal to Fg1 plus Fg2, times x1 times x2 plus, and then go on and on all over the total weight, sum of all the weight, if you want to put it like that. I want to rewrite that again just with this problem in mind. So the center of gravity is equal to Fg1 times x1 plus Fg2 times x2 plus Fg3 times x3 all over Fg1 plus Fg2 plus Fg3. Now, an important thing to note is what are these x's? Well, these are measured relative to the shoulder joint. Why? just because the problem gave these measurements relative to the shoulder joint. That could be relative to anything. It's just remember that when your answer comes out, whatever that distance is, that's the distance measured from the axis point that you chose. So XCG is equal to FG1, which is 17 newtons, times X1, which is 0.13 meters, plus FG2, 11 newtons, times the distance to that point, which is 0.38 meters, plus 4.2 newtons times 0.61 meters, all over the total weight, which is 17 newtons plus 11 newtons plus 4.2 newtons. Do the math there, and you get your answer as 0.28 meters. That is 0.28 meters from this shoulder joint. Okay, so we're now moving on to talking about topics involving moment of inertia. So in this case, a baseball pitcher pivots his extended arm about his shoulder joint, applying a constant torque of 180 newton meters for some duration of time. Now, as we discussed in class, this makes much more sense for a softball, where they're swinging their straightened arm in an underhand fashion. All right, so we have an arm, and it's moving with some angular velocity, with some torque in that direction. It could be positive or negative. In this case, since I'm imagining the underhand motion of a softball pitch, and if this is the body here, I don't know. In this case, it's going to be counterclockwise and therefore positive. Of course, you could always say you're looking at the person from the other side, in which case it's negative, but it's not going to be an issue for this problem. So we'll talk about the torque is 180 newtons times meters. The time duration is 0.10 seconds, and the moment of inertia equals 0.50 kilograms meters squared. What is the arm's angular acceleration and final angular velocity? Well, angular acceleration is easy because we're just going to use Newton's second law analog for rotational motion, which is torque equals I alpha. And we're looking for alpha. So alpha then is equal to torque over I. There's only one torque here, which is equal to 180 newton meters over 0.50 kilogram meters squared. So alpha is equal to 360 radians per second squared. Now find his final velocity. Well, if you remember this very simple kinematic equation, the final angular velocity equals the initial angular velocity plus alpha t, which is angular acceleration times time. We'll assume it starts from rest. That means the original angular velocity is 0. And alpha, we've already got solved for final angular velocity. That equals alpha t, which is 360 rads per second squared, times t, which is 0.10 seconds. So omega f equals 36.0 rads per second. So that's part A. Part B says find the final speed of the ball relative to a shoulder, which is 0.80 meters from the ball. So there's the shoulder. We want to find this velocity tangentially. So then we know that Vt equals r omega. So that's just going to be 0.80 meters times omega, which we just found, 36.0 rads per second. So the tangential velocity equals 28.8 meters per second. And another one here. A large fish strikes bait cast by a fisherman with a rod and reel. The fish creates tension in a line of 65 newtons. How many revolutions of the reel occur in 1 second if the reel has a moment of inertia at that and a radial distance of the line from the reel axis is 4 centimeters? Okay, well this just this is a kinematics problem. I can think of my reel of radius r, and I can think of the line here that's drawn in. The torque, the tension is in that direction, and I want to know how many revolutions. So what I'm really talking about is what angular displacement, right? So let's go through all our variables. Theta 0, we're going to set to 0. Theta final, we don't know this. That's the one we're looking for because we want to see how many revolutions. So omega 0 equals 0 because the reel is not moving before the fish strikes the bait. And finally, it equals, well, we don't know that either. And alpha, we don't know that. Delta t equals 1.0 seconds. That's what we're given. And we're also given that the moment of inertia equals 4.0 times 10 to the negative third kilograms meters squared, and that the radius right here, r, is equal to, well, I'll just say 0.040 meters. Well, we have this equation, theta minus theta 0 equals omega 0 t plus 1/2 alpha t squared. Now we don't have alpha right now, but we can find it. Let's just, keep that in mind. We know the initial velocity is 0. We know the initial angular position is 0, so theta equals 1/2 alpha t squared. All right, so all we have to do is find an expression for alpha. Well, we know Newton's second law for rotational motion is I alpha, sum of all torques equals I alpha. Solve for alpha, that means the torque applied by this tension over the moment of inertia is equal to alpha. So now we have everything we need. We have theta equals 1/2 tau over I t squared. Okay, or theta equals 1/2. No, we don't. We have to find torque now. But we know torque is equal to RF sine of phi, or in this case, it's just R times T, where the tension is, and the angle there between the radius and the tension as it's connected is phi, which is 90 degrees. So that goes away. So torque is just RT. So it's R times tension over the moment of inertia times T squared. Now we can plug numbers in. So that equals 1/2 of the radius, which is 0.040 meters, times the tension, 65 newtons, over 4.00 times 10 to the negative third kilograms meter squared, times the time duration, which is 1.0 second squared, and theta is equal to then 325 radians. Question asks for revolutions. So let's multiply that 2 pi radians in any one revolution. and that is equal to then 51.7 revolutions. Okay, so this is a little bit of a tough one because this is not, well, things are moving. This is not just statics anymore. So we have the combined moment of inertia of a dual pulley is 50 kilogram meter squared, and the crate at the bottom of this pulley weighs 4,420 newtons. A tension of 2150 newtons is maintained in the cable attached to the motor. Find the angular acceleration of the dual pulley. All right, so this is a tough one where we're going to have to first draw a bunch of diagrams and write down all the stuff that we know. So we have tension working this way, and I'm going to call that T1 because we have another tension here, T2, which attaches to this block of some mass, and that experiences the force of gravity downward. So we know T1 is equal to 2150 newtons. And we know the force of gravity is equal to 420 newtons. And let's see, we had the moment of inertia. The pulley is 50.0 kilograms meter squared. We, let's say, don't know what alpha is. But that's probably going to be important. We have the radius of, okay, so we have the radius of the smaller section of the pulley. I'll call that R, maybe I'll call it R2 and call the larger radius R1. And that's given as 0.600 meters, and R2 is given as 0.200 meters. Let's see, we also know when it comes to the torque applied to this angle is going to be 90 degrees with the radius, right? And so, well, this angle, that will be 90 degrees with the radius. So phi1 equals phi2 equals 90 degrees. And therefore sine of phi1 or phi2 is going to equal 1. All right, so we've written down a lot of the stuff that we know. Let's take this little scenario right here and expand on that. We know the sum of the forces in the y direction is going to be equal to the T2 tension minus the force of gravity, which is equal to mass times acceleration in the y direction. Right? But whatever this acceleration is, that's going to be equal to the radial acceleration over here. Right? Or, well, this is going to be equal to r alpha, because whatever acceleration in this linear distance here, it's going to have to equal the angular acceleration of that small section of the pulley. And this R is going to be R2 because it's that small pulley. So the sum of these forces is T2 minus Fg equals mR2 alpha. Oh, I said I think alpha is going to be important. It's because alpha is what we're looking for. Sorry. Okay. So I can solve this for T2, which is just mR2 alpha plus the force of gravity. Now, why did I solve for T2? Well, because now we can look at the torque involved on the pulley system. So the sum of the torques there is equal to T1, which is counterclockwise, so it must be positive. Well, there's tension 1, I'll call it torque 1 for that, corresponding to that tension. And tau 2, which is going to be negative because it's going to be induce a clockwise torque. Now, we know that this is not at equilibrium. This does not equal 0. We can, however, say that the net torque will for sure equal I alpha. Okay, so T1, which is R1 F1 sine of phi1, minus tau 2, which is R2 F2 sine of theta 2, is equal to I alpha. And of course the signs go away because the angle is 90 degrees. So R1 F1 minus R2 F2 equals I alpha. And I can just say F1, I should have wrote in there, is just the tension 1 minus R2 tension 2 equals I omega. Okay, well, we have tension 1, we don't have tension 2, we don't have this, we're looking for it, we have the moment of inertia, but what do we have for T2? It's up here. So R1 T1 minus R2 T2, which is mR2 alpha plus FG, equals I omega. And we can then just do some algebra. We have to separate alpha. But unfortunately, there's an alpha term over here. So I'm going to expand all this and move this term over to the left. So R1 T1 minus RM, oh, wait. This is R2, excuse me, left that out. So that would be this times this term, which is going to introduce R2 squared. So it's going to be mR2 squared alpha plus, oops, sorry, negative, because the negative sign has to be distributed to the other term as well, minus R2FG minus, because I'm bringing it over, I alpha equals 0. It equals 0 now because I brought this term over to the other side. The sum of the torques does not equal 0. Don't get confused there. So then I'm going to say R1 T1 minus R2 FG, and now I'm just left with these two terms involving alpha. They're both negative, so I'm going to say minus alpha times positive mR2 squared plus I equals 0. And so that means alpha times mR2 squared plus I equals R1 T1 minus, well, that would be plus R2 FG. No, it wouldn't. Excuse me. This would be minus, because all I did was move this term over to the other side. These terms stay the same. So then alpha, we can say, is just equal R1 T1 minus R2 FG all over mR2 squared plus I. And we have our answer. It's just a matter of plugging in numbers now. Times the tension is 2150 newtons, minus R2, which is 0.200 meters, times the force of gravity, which is 4420 newtons, all over m, which, oh, unfortunately we don't have the mass. Oh, that's a pain in the rear. So we have to say the force of gravity equals mg, and the mass equals fg over g. So if I put that in here, whoops, I have the force of gravity, which is 4420 newtons over 9.8 meters per second squared, times R2, 0.200 meters squared, plus the moment of inertia, which is 50.0 kilogram meters squared. And alpha then, when you calculate all that out, equals 6.3 radians per second squared. Okay, so we applied some of Newton's second law for rotation. Let's explore the moment of inertia a little bit. This should say each have mass m. So these two particles are equal mass, and they're connected by a rigid thin rod of length L. And we're just going to ignore the mass of the rod itself. I should probably put that in there. All it's doing is connecting the two point masses. So we have two different situations. It's the same physical thing, but one in which the system rotates around this axis point through one of the masses, and the other where the system rotates around the central point between the two masses. Okay, so part A, we know that the sum of all the moments of inertia is equal to the sum of mr squared, where I just put m as a subscript, like m1 r1, m2 r2, that kind of thing. In this case, that equals m1 r1 squared plus m2 r2 squared. We know these two masses are equal, so that's just like saying m times r1 squared plus r2 squared. Well, what is r? R is the length of the rod, so that equals m times L squared plus L squared. I'm sorry. Take that back. Ooh, back it up. R1 is 0 because the axis goes right through that. So the distance between the mass and the axis is 0. R2, however, is equal to the length of the rod. So the sum of the moment of inertia, the total moments of inertia, are just ml squared. Now, if we look at the other situation, sum of the moments of inertia equal m1 r1 squared plus m2 r2 squared, just like before, equals m times r1 squared plus r2 squared. But now the distances have changed, and now each side is L over 2. That is r for each mass. This equals m times L over 2 squared plus L over 2 squared, which is just equal to, well, I'll write it like this, times L squared over 4, because I just squared everything inside the parentheses, plus L squared over 4, which equals m times 2 L squared over 4, because added those two things together, which just equals 1/2 ml squared. So you can see these two situations produce a much different moment of inertia, even though it's the same physical thing. It's just you change the axis and the moment of inertia changes. All right, so we've got a dart player here that holds a dart with her forearm initially in a vertical position. She quickly accelerates the forearm forward and releases the dart, holding the upper arm fixed. Find the by muscles connecting it to the upper arm in order for the dart to leave the hand with the speed of 12 meters per second after the forearm has rotated through an angle of 0.3 rad. The radial distance from the dart to the pivot point at the elbow is 0.4 meters. Treat the forearm as a thin rod of mass 2 kilograms and length 0.4 meters. So we've got an arm here with the elbow right there. And we have the forearm, which we're treating as a thin rod with the dart in her hand, and there's going to be a torque applied in that direction and a final velocity in that direction. Okay, so let us write down everything we need to know. We need to know the final tangential velocity is equal to 12.0 meters per second. It's rotated through an angle of 0.300 radians. The length of her arm, which I'll call R, is equal to 0.400 meters, and the mass is equal to 2.00 kilograms. What is the torque? Well, this problem to me screams of a kinematics problem. But let's see, we can find the angular acceleration through kinematics, but then we know that's related to torque by Newton's second law, or the analog of Newton's second law. So let's do that. If you remember this equation, okay? Everything's starting from rest, so that equals 0. The initial angle we're going to set equal to 0. So I can just now solve this for alpha, where alpha is equal to omega f squared over 2 theta. Okay, but what is omega f? Well, the tangential velocity is just equal to r omega, so omega equals Vt over r. Let's plug that in. So alpha now will be equal to 1 over 2 theta times Vt over r squared. So now we have an expression for alpha in terms of theta, which we have, the final velocity we have, the radius we have. So now we can find the torque, because we know the torque is just equal to I alpha. And we have, do we have I? No, we don't have I. But we know that it's a thin rod, so if I look up at my chart, I can find that I equals 1/3 m r squared. And, all right, so I'm going to write it over here. Torque is equal to I, which is 1/3 m r squared, times alpha, which we now know is 1 over 2 theta times Vt over r squared. Whoops, bracket. So I'm going to do some algebra arranging. We've got 1/3 times 1/2, so I can pull that out and say 1/6. We have masses by itself, but r squared times divided by r squared, oh, that cancels out. And Vt is left, but theta is in the denominator. So I can write that a little neater. mVt squared over 6 theta. The torque is equal to the mass, 2.00 kilograms times Vt squared, which is 12.0 meters per second squared, over 6 times 0.300 radians. Torque is then equal to, oh, did I not calculate it out? Okay, so let's see, that's 144, so that 2 times that will be 288, and 6 times 0.3, that would be divided by 1.8. So it's going to be somewhere around 144 Newton meters. Well, I guess I can divide it out. So that's 1. 18 goes into that 5 times 1.5. So it's going to be I'll have to look up that answer, but this is the expression you're looking for. Oh wait, I have a calculator here. So let's see. 12 squared is 144 times 2 divided by 6 divided by 0.3. It's around 160. Newton meters. All right, we are now getting to finally to rotational kinetic energy, which is equal to 1/2 I omega squared, which is very close to kinetic energy in the translational sense, which is 1/2 mv squared. But anyways, the problem says we have a hollow cylinder and a thin and a solid cylinder starting from S at the top of the incline. Determine which cylinder has the greatest translational speed upon reaching the bottom. What is the mass? We don't know. Where's the blank piece of paper? Okay, we don't know what the mass is. Let me just draw the whole situation. The original height, final height. It's going down. It's theta. So we're not given a lot of numbers here. We're just going to have to solve this symbolically. Now we start with the work-energy balance. Work non-conservative equals the change in energy, which equals 0, because there's no non-conservative work here. So we say that energy initial equals energy final, and then kinetic energy translational plus kinetic energy rotational, because now we have a second kinetic energy to add into this, plus potential energy, oh, and these are all initial, equals kinetic energy translational final plus kinetic energy rotational final plus PE final, which is like saying 1/2 m v naught squared plus 1/2 I omega naught squared plus mgh0 equals 1/2 mv final squared plus 1/2 I omega final squared plus mgh final. Well, we know a few things right away. These go to 0 because it starts from rest. And then we are left with, oh, we also have 0 potential energy at the bottom. Because we could define it that way, and that makes our problem a lot easier. So mgh0 equals 1/2 mv final squared plus 1/2 I omega final squared. Okay, well, we have angular momentum and we have, or angular velocity and linear velocity in the same problem. How are we going to deal with that? Well, since it's rolling and it's not slipping, if you remember the stuff we covered before with the rolling motion, how this arc length from A to B must equal this path length of the center from A to B, because if you just like cut open the tire and lay it down flat, it would stretch that distance. So the distance traveled is going to equal the arc length s. So we can also say that the velocity translational is going to equal the velocity tangential. And we know how to find the tangential velocity because tangential velocity is just r times omega. And it's going to be omega final because that's what we're plugging in here. Or we can say omega final is equal to Vt over r. And plug that in. Bring everything down. Mgh naught is equal to 1/2 m Vf squared, which again is the same thing as Vt. So I'm going to write that as such. Vf over r squared. I wrote Vf because Vf is the same as Vt because it's rolling without slipping. One other thing, we have to look at, well, let's not do that. Let's leave the moment of inertia as it is for now. So we'll solve for a general expression involving the moment of inertia, and then that's the only thing different between these two shapes, so we'll plug that in at the end. We are looking for V final. So this is equal to V final squared times 1/2 m plus 1/2 I over r squared. I just pulled V squared out of each term. So now then, Vf squared is equal to 1/2 m plus 1/2 I over r squared. Whoops, no, excuse me. That's the denominator. It's equal to mgh naught over 1/2 m plus 1/2 I over r squared. And then V final is just equal to the square root of mgh naught over, maybe I'll pull out the 1/2 m plus I over r squared. So what should we note here? Well, we should note here that I is in the denominator. So as the moment of inertia increases, the velocity should decrease. And which one is going to have the higher moment of inertia? Well, it's going to be the hollow cylinder, because the hollow cylinder has all of its mass spread out along the outer edge of the shape, whereas this has mass spread out at all different radii from the shape. So this is going to have more of its mass closer to its axis of rotation than this will have. So this will have the larger moment of inertia. So this should reach the bottom last. So this is first, this is second. But let's take another look at it. So for a hoop, we know that I equals mr squared, so I can plug that into the equation for velocity. So Vf equals square root of mgh final over 1/2 m plus mr squared over r squared. So this simplifies nicely because these r squareds cancel out. M plus m is 2m times 1/2 is just m. And then, well, I'll carry it out. So that's mgh over 1/2 2m. 2 times 1/2 cancels, m times m. So Bf is just square root of gh, which is gh initial. Pretty simple. So for the cylinder, I then is equal to 1/2 mr squared. That's just what I look up from a table. The F then is equal to mgh0 over 1/2 times m plus 1/2 mr squared over r squared. Well, the r squareds are going to cancel out, and we'll be left with mgh0 over 1/2 m plus 1/2 m. So that's 3/2 m times 2, times 1/2. mgh0 over 1/2 times 3/2 m. Okay, so these two m's cancel out, and we're left with the square root of gh0 over 3 over 4 in the denominator, which is the same as saying that equals the square root of 4 over 3, because I flipped that, it's in the denominator, I'll bring it up to the numerator by flipping it, times the square root of gh0. So then, the cylinder is going to have, well, I can put it like this. Square root of 4 over 3 times Vf for the hoop. So this is going to be larger for the cylinder by a factor of square root of 4 over 3, which is greater than 1.